Automated classification libraries in Python evaluate a machine learning model in seconds. But relying on prepackaged functions leaves the mechanics of those evaluations hidden. To really understand how these models are judged, we are going to build a complete binary classification evaluation toolkit from scratch using standard Python. Step by step, we will construct the confusion matrix, program the standard scoring formulas, and write a custom generator for the ROC curve. By reverse engineering the math, you gain the precise knowledge needed to justify model performance to stakeholders. This Jupyter notebook begins with our basic environment setup. We import the standard PyTorch, NumPy, and Matplotlib libraries. Looking at this cell, we generate our dummy data. We use the make classification function to create a two-class problem, and we add uniform noise to make the separation slightly more realistic. This scatter plot displays the distribution we just generated. You can see two distinct clusters, the positive class in yellow and the negative class in purple. We will train a simple PyTorch logistic regression model to divide these two clusters. The model will output probability scores, which we will use to test our custom metrics. The foundation of all classification metrics is the confusion matrix. It tracks exactly how the model's predictions align with reality. By setting a strict probability threshold, like 0.5, anything above the line is predicted positive, below is negative. Correct positive predictions tally a true positive. Correct negatives are true negatives. The remaining spaces capture errors, false positives, and false negatives. These four exact counts, true positive, true negative, false positive, and false negative, form the raw inputs for every evaluation metric we are about to write. We start with accuracy. This metric simply measures the total number of correct predictions divided by every prediction made. In Python, we define a function that adds the true positives and true negatives together and divides that sum by the total count of the matrix. Accuracy alone can be misleading. To understand reliability, we calculate precision. It divides true positives by all positive predictions, isolating false positives in the denominator to measure how often the model cries wolf. Next, recall answers a different question. Out of all the actual ground truth positive cases, how many did our model find? To compute this, we divide true positives by the total actual positives, isolating false negatives. Looking back at our scatter plot, recall evaluates how many of all the yellow dots we captured. Precision looks only at the specific zone the model labeled positive and evaluates how many purple dots accidentally slipped in. Because optimizing for recall often hurts precision, we calculate the F1 score. This is a harmonic mean that balances both metrics into a single number. All of these scores share one limitation. They only evaluate the model at a single, static probability threshold. To see the full picture, we need a dynamic way to evaluate performance across all possible boundaries. The receiver operating characteristic, or ROC curve, visualizes performance across all thresholds simultaneously. We define an ROC curve class that iterates through threshold values, starting at 1.0 and stepping down to 0.0. At each stop, it recalculates true and false positive rates, plotting coordinates to draw a continuous path. This plot displays our final custom ROC curve in blue. The higher it arcs above the red dashed line, which represents a purely random guess, the better the model is at separating the two classes. Here is a slightly different styling, using a green line to map those exact same true and false positive rates. To quantify this curve, we calculate the area under the curve, or AUC. A perfect model scores a 1.0, while a random guess scores a 0.5. This output prints our custom ROC AUC score. The math confirms our model has strong predictive power, and we proved it without relying on a black box package. You have successfully built the core evaluation metrics for binary classification entirely from scratch. Try adjusting the uniform noise parameters in the initial dataset generation cell. As the data gets messier, you can watch the ROC curve flatten toward the random baseline. Knowing the raw mathematics behind these formulas ensures you can accurately defend your model's performance in any production environment.